The next type of circuit that we're going to consider are Zener Diode circuits. And so typically Zener Diode circuits are going to be used as a reference voltage or to regulate a voltage. And what we're going to see in later classes is there are more sophisticated ways that we can regulate voltage, and typically that's going to involve integrated circuits or ICs, but we're going to get a basic idea for the principles with our Zener Diode circuits. So let's consider this simple circuit here where we have a constant DC voltage source, or VPS for our power supply. We have some input resistance R sub I. A Zener diode, we can tell it's different from a normal diode because we have sort of the little squigglies on the end of it there, and a load resistor RL with some voltage across it. So let's define a few other things here. So first of all, let's put in our diode voltage and current. So I'm going to put VZ for our Zener voltage. I'm going to put IZ for our Zener diode current. And so you might be noting that I seem to have drawn these in backwards. So why have I done that? And so the reason is, if you recall from our first unit, our Zener diode is actually designed to operate in the breakdown region. So Zener diode is designed to operate in breakdown. And so just to give us a little bit of a refresher, let's look at our IV plot, or our current voltage plot for a diode in general. So remember, we have our forward biased over here on this side, so this would be our forward biased, and then over here we have our reverse bias characteristics. And so if we push it too far in reverse, we get this area called breakdown. And so this is actually where our Zener diode is designed to operate. So you might be asking yourself, why would we ever want something to operate in breakdown? Well, the advantage of it for the Zener diode is, if we note here, if we're looking at our breakdown region, we can move up and down this region, changing our current while keeping a relatively constant voltage. And so let's go back to this first sentence I wrote up here, that our Zener diodes are going to be used to regulate our voltage, or to have a reference voltage. So what we can do is we can say, well, we know this Zener diode has some voltage VZ, and because of that, if we put it in parallel with something, then that should also have that same voltage VZ. So that's kind of the idea we're going for. So that's why we have our voltage and current defined backwards, because these are, of course, negative values, negative current and negative voltage. So if we switch the direction, we can still be talking about positive values. So let's define a couple other items on this circuit to make our analysis easier a little later on. So let's define some input current I sub I and some load current through our load resistor I sub L. Okay, so I think we've got everything we need defined here now. So the basic idea with this, so let me move this down a little bit to make some space so we can still see our circuit. Okay, so our basic idea here is we want that load voltage to stay the same. So want VL to stay constant. Now, we want it to stay constant even though there might be other things changing in the circuit. So we might have RL changing, and we might have VPS changing. So again, the key thing is we want this VL to stay constant even if we have RL and VPS varying. Now, why would our RL and VPS be varying? Well, let's think back to our ripple voltage from our rectifier circuits. So we could think about our ripple voltage as being sort of the input here. So we have some ripple, so maybe it is going something like this, so it's not just a constant DC value, and we don't want that sort of fluctuation to translate into our output. So we're kind of looking at that regulation stage from that introduction video we talked about back at the start of the unit. So that's how our VPS could vary. Now what about our RL? Why would that be varying? Well, there's a lot of reasons our RL could vary. We're going to look at an example in the next video where we talk about a radio. Depending on how loud the sound you're outputting is, you're going to have a different load resistor. The same basic idea could be applied to, for instance, elements that heat. So the more heat you're producing, you could have various resistance values. Okay, and then one other note too is that we have this Ri resistance in here, this input resistance, which is just going to limit current through our Zener diode. We do want some kind of safeguard in there to protect our diode. Okay, so now let's look at some analysis. So what we're going to do is we're going to start with sort of some basics here. We're going to do KVL and KCL. So from our KVL, we're going to be, of course, we can say that we have a voltage drop across our Ri that looks like this, such that we can use positive sign in any IV equations from passive sign. So we can do a KVL loop around here to solve for that R sub I value, and we'll play some games with that. And then another sort of key thing we're going to use a little later on is we can do KCL here to relate our three current values. So again, you've got the handwritten notes posted on Canvas, so you can be looking at that image as I'm going through and writing these equations. Okay, so first of all, let's start with our KVL around that loop. And again, you can start at any point, go in any direction. But what we have from KVL is we have negative VPS plus our input current times our input resistance plus our Zener voltage is equal to 0. So we can solve that for our R sub I. So VPS minus VZ divided by our input current. And now if we use that KCL relationship, we can rewrite that as VPS minus VZ divided by I sub Z plus I sub L. And let's call this, to be consistent with the notes, equation 1. And so these equations are kind of going to look a little random as far as why I'm doing certain things, but basically we're building up to an equation that we can use in this type of Zener diode circuit. Okay, so let's rearrange this equation 1. We can solve it for IZ, our Zener diode current. And so we can say that's equal to VPS minus VZ over R sub I minus IL. And again, consistency with notes, I'm going to call this equation 2. So remember, for our Zener diode to operate properly, it has to be in the breakdown region. So Zener diode must remain in breakdown region. And so what that means practically is that we're going to have boundaries for our current upper and lower boundaries. So boundaries of IZ min and IZ max. And so coming back to our IV curve here, of course, ideally we could just stay on that highlighted line forever, but if we go too high, if we have too much current, we can of course break the device. And if our current gets too low, then we're going to start seeing variations in our voltage. So practically we're going to have some bounds, IZ min and IZ max. So we've not set any restrictions as to what those are right now. We're just saying somewhere those bounds exist. So now let's consider those two boundaries in the context of equation 2. So in the context of equation 2, we can say, let's consider our IZ min first. So if we want a minimum Zener diode current, looking at this equation 2, we can say if we want this to be small, we want our VPS to be small, and we want our IL to be large because we're subtracting that. So coming down here, we can say that corresponds then to a VPS min and an IL max. And so through similar arguments, we can say that our IZ max, if we look at equation 2 above, corresponds to VPS max and IL min. Okay? So now what we can do is we can take both of these and consider them in terms of 1. So consider in our equation 1 above. So now I'm just going to basically plug in, because we're going to have different VPSs, different IZs, and different ILs. And we're assuming that our VZ is going to remain constant. So plugging that in, and I'll try to keep that on the screen there. So we have our RI for that first case, so let's look at this one first, is equal to VPS min minus VZ divided by IZ min plus IL max. Okay, let's call that equation 3. And then if we do this second case for our IZ max, we can say Ri is equal to, we're going to have VPS max, so basically everything's just going to swap here, minus VZ divided by IZ max plus IL min. Let's call that equation 4. So obviously what we can do now is we can equate equation 3 and equation 4 because both of those are expressions for Ri, which of course should be the same. So equating those two, we then have the following. We have VPS min minus VZ times IZ max plus IL min. This gets a little bit messy, but bear with me, it won't be too much longer, is equal to VPS max, so basically just going through this algebra here, minus VZ times the quantity of IZ min plus IL max. All right, and let's call that equation 5. Okay, so typically, let's think about sort of a typical problem, and so we'll see this in the example in the next video, but typically for a problem, we're going to know several of these values. Let's clean that up a little bit. So typically, we are going to know the following. So we're going to know our range of the input voltages. So for instance, if we said it's coming off of a rectifier circuit, maybe we've done calculations, so we know what the range of our input voltages are, so that means we're going to know VPS min and VPS max. Okay. And also, we're usually going to know sort of the range of our load resistor. So that coupled with the range of sort of our Zener diode voltage, we can figure out the range of our load current. So this is another thing that we usually know. So range of load current, and of course that is our IL min and our IL max. Okay, and of course typically we're going to know also our Zener voltage. Typically, again, that's going to be fairly constant based on this IV curve if we're staying within our current limits. So we're going to choose our Zener diode based on our Zener voltage. So coming back up to this equation then, we can see what that leaves. So we're saying we know this, we know this. We typically know our IL, we know our VPS max, we know our VZ. And so basically we see we're left with two things. We're left with our IZ min and our IZ max. So what we want to do to sort of make this equation more useful is we can sort of make some minimum requirement. So for our minimum requirement, let's just somewhat arbitrarily say that IZ min is equal to 1/10 of IZ max. So IZ min equals 0.1 of IZ max. And so let's call that equation 6. So what we can do then is we can substitute equation 6 into equation 5, and then we can just have an equation that we sort of just go to whenever we're dealing with this Zener diode circuit. Again, this is for this particular circuit, but we could use similar ideas to easily sort of expand this to different Zener diode circuits. So we have IL max times the quantity of VPS max minus VZ minus IL min times the quantity of VPS min minus VZ. And all of that is going to be divided by VPS min minus 0.9 Vz minus 0.1 Vps max. And so that would be the equation we use if we see this circuit. One thing that I didn't mention earlier on that I should have is that we're assuming that we have an ideal diode with 0 Zener resistance. We can, of course, expand that to include a non-zero Zener resistance. If you want to see how that's done, you can look on pages 88 to 90 in the Neiman textbook. So what we're going to do in the next video is we're going to come back and we're going to use this equation in an example, and then we're going to move on to other types of diode circuits after that.